Math 2312, Chapter 1, Functions, Section 1, Functions and Function Notation, Video 4, Graphing a Function. In the first video, I mentioned that there were several ways to represent a relation. And remember, a function is just a relation with a special condition. And one of the ways to represent a relation is a graph. Well, since a function is a relation, it stands to reason that we can represent it as a graph as well. But the big question is, how do we go from a function, and specifically one in function notation, and rewrite it as a graph, or draw it as a graph? Some people cringe at the idea of graphing because they think that it's difficult to do. The truth is, the basic premise behind graphing is so simple, but there's a reason why people struggle with it. The reason people struggle with graphing functions is they have trouble making decisions. Seemingly random decisions. I'm going to give you a procedure that when followed through enough will graph anything. It's just not the most efficient approach. Later, for different categories of functions, we'll learn more efficient ways to graph them aside from this universal technique that I'm about to show you. The premise behind graphing is really pretty simple. Connect some dots. The reason people have trouble is they don't know where to get the dots sometimes. So without further ado, I'm going to give you a 4-step process that will graph any function. Step number 1, select any value and substitute into the function. Actually, this is kind of 2 steps. You select a value and then you substitute it into the function. Now we're going to be doing this repeatedly, so let's organize our work by making a table. Since our input is called x, we'll label the first column x, and since we're evaluating f of x, we'll call the second column f of x. We could also call it y. In fact, there are some authors that will say f of x is just a fancy name for y, but that's under the premise that the input must be x and the output must be y, which isn't always the case. Input and output's the best way to think about it. Then pick a value and substitute it into the function. Let's start simple. Let's substitute 0. If we put 0 into the function, we'll get 0 to the 3rd power minus 4 times 0, and without much to do, it comes out to be 0. What that gives us is an ordered pair. So, step 2. Plot the resulting ordered pair. Remember, when you evaluate a function numerically, the input is the first coordinate and the output is the second coordinate. That means that the ordered pair 0, 0 represents a point on the graph of this function. Well, now what? Well, this isn't much to go on. If I were to come over here and draw an x and a y-axis, and again, I'm assuming that you're familiar with graphing basics. Being a pre-calculus class, you've seen some algebra, and graphing is a part of it. 0, 0 is the origin. This isn't enough evidence to find our graph. Our 3rd step is repeat 1 and 2 until the graph emerges. In other words, do this until you see enough dots to connect smoothly. This is where people struggle with graphing. What do I pick next? The truth is, it doesn't matter. Well, what do I pick? I don't care, pick something. But I don't know what to pick. Just pick a number. My advice, though, is don't go crazy. 0 is always good. I would hover around some small numbers to begin with, like 1. If we substitute 1 into the function, we'll get 1 cubed minus 4 times 1, and without dilly-dallying, this is 1 minus 4, which is negative 3. The point 1 comma negative 3 is on our graph. 1, negative 3, is about here. I'd say that's not enough evidence. If you tried to connect them and make a line, that is a graph that goes through those 2 points, but I know this isn't a line. I know exactly what the graph looks like, but if I didn't, I'd still want more evidence. What you're looking for is enough evidence to capture the curvature and the location of the graph, whatever those things mean. So let's pick another number. Well, we picked 0, we picked 1, why not pick 2? We substitute 2, we get 2 cubed minus 4 times 2. 2 cubed is 8, but so is 4 times 2. 8 minus 8 is 0. We've located an x-intercept. The point 2 comma 0 is right here. At this point, you might think it might be a parabola, and you're getting closer, but I'd still like some more evidence. Now, if you knew in advance what shape to expect, and at the right time, we will know in advance what shape this graph would be, then we would keep tracking down enough evidence until we found that shape. But trust me, right now, it's not there yet. So this is why people struggle with graphing. I don't know when to stop. Well, if you're doing it with no previous information, you just keep going until you find it. But as we go through this course for different types of functions, we'll know things about them in advance and we'll know what to look out for. For example, I know not only exactly what this graph looks like, but where it's located. I kind of picked it that way. We need more evidence, so let's get more inputs. I guess 3 is a good place to go next. We put in 3, we get 3 cubed minus 4 times 3. This is 27, this is 12, 27 minus 12 is 15. And at this point, my outputs are starting to get kind of large. The way this coordinate plane is drawn, I really don't have room to go up 15. I guess I can count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. About up here around the T. And we would have this point over 3 and clear up here. And I'm afraid that as I go further, it's going to get larger and larger. I could confirm that by picking 4, substituting in there, and getting 48. All right, I think I know what's happening as we go further. This graph's just going to skyrocket, and I really don't want to draw any more points up in the sky. But wait a minute, we're totally not looking at the left half of the graph, where the x's are negative. So let's pick some negatives, like -1. I'm going to spare the details and just tell you that when I substitute -1, I'll get 3. I invite you to verify that, but I promise you, putting in -1 will get 3. That point's a little bit manageable. It's right there. Okay, I'm starting to see this parabolic shape, so maybe it is a parabola. But let's look for more evidence. Again, you really shouldn't make any assumptions unless they're already established facts. Most of you know that parabolas come from x-squared functions, from quadratic functions, and this isn't one of them. I'm not expecting a parabola. If I substitute -2, and again, I strongly recommend verifying what I'm about to tell you, but if I substitute -2, I'm going to get 0. Don't believe me? Check it out. So this thing that looked like a parabola suddenly is turning around. Over here, when it turned around and hit the x-axis, it skyrocketed up. Going backwards, it turned around and hit the x-axis. I wonder if it's going to skyrocket up also. Let's check by putting in another negative number and getting some more evidence. Again, sparing the details, if you substitute -3, you'll get -15. Don't believe me, check it out, but I promise you, -3 will give me -15. And at this point, some of you might start thinking, wait a minute, is it this because it's that? In general, no. For this specific example, yes. But again, the more you know in advance, the less work you have to do to graph a function. I know a lot of things about this function, including the fact that opposite inputs were going to give me opposite outputs. Like the 1 and -1 gave opposite outputs, and the 3 and -3 did. Technically, so did 2 and -2, but 0 is its own opposite. But I digress. When we put in -3, we're going down 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, all the way down here at the bottom of the board. And although it's a pretty tight squeeze, I'm thinking about connecting these from left to right. Starting low, it's pretty steep, but at some point it's going to have to hit this point up here and turn around and hit the origin. Now, I don't know if it actually turns around at this point. That would require some calculus. So for now, let's just assume that it does, turns around and hits the origin, but then it has to come hit this guy down here. Then it has to turn around, cross the x-axis again, and then skyrocket up to hit that point. If you were wondering if it would turn some more on either end, we could seek evidence by putting in larger positive values or lesser negative values, but you would find out that the right side is going to continue skyrocketing, whereas the left side is going to continue plummeting, and here's our graph. I don't recommend graphing all functions this way. I'm sorry, I left off step 4. Connect the dots. Most of the time when you connect them, it's smooth and continuous. Smooth means no corners. Continuous means not broken. But soon we'll see examples of graphs that have corners and are broken. But unless you run into an exception, you assume that when you connect them, it's smooth and continuous. And again, it's not the most efficient way to graph a function. In fact, I would call it a last resort. But it's the universal way that will always get the job done. The more efficient approaches only work at certain times. This works always. You just have to be persistent. Well, I say always, there are a couple of minor examples. But as long as there's no numbers that have issues when you substitute them into the function. In other words, as long as every number is in the domain is all real numbers, you can do what's called plug and chug. Plug in values, chug out the answers, plot and connect.